Welcome back. This is 6.2.3.3a. We are going to perform the discrete time Fourier transform of this single pulse sequence. It is an even function, it is symmetrical, and it has finite support from -4 to 4. Since this is aperiodic, we can only apply the DTFT. We can use this equation directly by setting from n equals to this position, -4, and the top one is +4, and we apply xn, which is all value of 1, so we are basically summing e minus j omega n. So this is a finite sum of a exponential sequence. You can write a software for this, and it is simply a for loop across these 9 samples and another for loop for different omega. Okay, we'll show you the code later on, and out comes these results. In this particular example, you can try from 0 to 0 to 2 pi for the omega, or if you prefer -2 pi to 2 pi just to see the 2 pi periodicity, or from -pi to pi, whichever you prefer. Now, we have always told you that x of omega is a complex number, and usually we plot the magnitude and the phase, but this time we're plotting x omega, and you realize that it goes to negative, because if you plot magnitude, there's no negative. Now, this is a special case when your function is an even function and therefore only real number for the x omega. So you have these values that is positive and these values that is negative, positive. Now, if you're going to plot magnitude and phase, then of course this negative value all become positive. Right, so that's the idea, and in the below you can see that I plot the magnitude, or as magnitude as absolute numbers, and to denote it as negative numbers we plot the phase. Now the phase is this is plus pi, of course, and this is minus pi, and what we want to say is -1 is equals to 1 e pi is equals to 1 e minus pi, and hence you can have positive phase or negative phase, and it's changing up and down due to numerical precision. So I wrote a program and simply I calculated this and I got this result. Of course, in the exams you do not have the computer to generate these numbers for you, so you have to write the closed form solution of the finite sum of this exponential sequence. Okay, so if you recognize that to get this is simply a manipulation of a finite geometric series, and I can provide the details in the next page for you. Okay, so what you should do is first to substitute the starting point and the ending point as variables, and then you are going to perform the summation across only this finite support where there is non-zero, and you substitute r as this complex variable e minus j omega, and then so simply we are doing this sum. So now it becomes a little bit simpler, and you begin to manipulate this sum. Okay, out comes finally this is the solution, which is r minus l, the starting point, minus r, l plus 1, the ending point, divided by 1 minus r, where r is e minus j omega. Alright, when you get this, then basically you can do a lot of manipulation such that finally you will end up with this very famous sine bracket some values divided by sine bracket part of this value omega over 2. Okay, so this is the sinc function. Later on you will see. Alright, so if you plot these values, you will notice that when omega equals to 0 is sine of 0 divided by sine of 0. So you have to be a little bit clever about it to get when the value is 0, how do you get 9? So you can have two tricks. One is of course the L'Hopital rule, and the other one is simply to use the for loop and you add up these 9 numbers, right? Because when omega equals to 0, you are adding up 1 plus 1 9 times. Okay, that's it for this page. Thank you.